Hello friends, welcome to another lecture of Laplace Transformation of Mathematical Physics, and this is lecture 7, and here we're going to discuss about unit step functions. So before we start, so let me tell you the link of previous lecture is in the description box. So if you want to watch that, you can watch that, and please like, share and subscribe this channel and hit the bell icon so that you get notified when new video is uploaded. So now let's start. The unit step function u of t minus a, it is defined as u of t minus a is equal to 0 when t is less than 1, when it is 1 when t is greater than 1, sorry, not 1, greater than equal a. Okay, so this is the definition of unit step function. So here you see, now Laplace transformation of unit step function is given by, so Laplace transformation u of t minus a, that's going to be equal to e to the power minus as by s. Okay, so now let me show you how to prove this. Okay, let me scroll down the page. Okay, let us prove this. Now if you find the Laplace transformation of unit step function u of t minus a, then by the definition of Laplace transformation, you should get integration from 0 to infinity e to the power minus st u of t minus a dt, right? You should get this. So now that's going to be equal to, so you can split this integral from 0 to a e to the power minus st u of t minus a dt plus integration a to infinity e to the power minus st e of t minus a dt, right? You can write this one like this. So now let me scroll down the page. Okay, so we know that when by the definition of unit step function for this function u of t minus a, it's equal to 0 when t is less than a, right? So from 0 to a, this is gonna be equal to 0, right? And for greater than equal to a, that means from a to infinity, the value of this function should be 1, equal to 1. So that's why we will get here this whole thing is 0 now. So we have a to infinity e to the power minus st 1 into dt. Okay, so since what we can write, since unit step function u of t minus a is equal to 0 when t is less than a, and it is equal to 1 when t is greater than equal to a, right? So we will get this result. So now if you integrate this e to the power minus st, then you should get minus e to the power minus st by s, and we have a here and upper limit is infinite. So if you put the limits here, then you will get the if you put infinity here, then you will get 0, then minus, then if you put a, right, if you put a here, then you should get minus e to the power sa by s, right? Then our result will be e to the power minus as by s. So that's the Laplace transformation of unit step function. This is the result. So this is nothing but Laplace transformation of unit step function. So that's how we can prove this. So hope you have understood this. Now let's move on to second shifting theorem. Okay, now second shifting according to second shifting theorem, if Laplace transformation of f of t is capital F of s, then Laplace transformation of f of t minus a into u of t minus a, that's going to be equal to e to the power minus a s capital F of s. Okay, so now let me prove this one. So here let us write Laplace transformation of f of t minus a dot u of t minus a, that can be written as by the definition of Laplace transformation, that's going to be 0 to infinity integration e to the power minus st, and the function is f of t minus a dot u of t minus a dt. That's by definition of Laplace transformation, right? So here you see we can now again split this integral from 0 to a and a to infinity. So 0 to a, so let me scroll down the page. 0 to a e to the power minus st f of t minus a dot, here it's going to be 0. Here you see this function, unit step function, it is 0 for less than t less than a. So that's why from when you write here integrals from 0 to a, so that's going to be 0 dt, right? And plus a to infinity, so its value will be 1 for greater than a. So if value of this unit step function is 1, so we will get e to the power minus st f of t minus a into 1 dt, right? So because since you can write here that unit step function of t minus a, it's equal to 0 when t is less than a, and it is equal to 1 when t is greater than equal to a. So hope you have got it. So that is why we have got this result. So when you write this limit 0 to a, so here the value of this function will be 0, and when you have a to infinity, integration a to infinity, then it's going to be this function going to be equal to 1, right? So hope you have understood this. Now this whole part is 0 now, so we have left with integration from a to infinity e to the power minus st f of t minus a d. Now let us substitute t minus a is equal to, suppose b, let us substitute b. Okay, then it implies t is equal to b plus a, right? T equal to b plus n, and as t tends to 0, sorry, not t tends to 0, t tends to a, then b tends to 0, right? So from here you see when t tends to a, then b tends to 0. So we can write this above result. This is Laplace transformation of f of t minus a into u of t minus a, sorry, so let me scroll down. Okay, so this result can be written as f of t minus a into u t minus a, that's going to be equal to, so instead of a to infinity, we're going to write now 0 to infinity, because when t tends to a, b tends to 0, and we have substitute t, instead of t we have put v, right? So our function should be our result should be s minus s into v plus a, and f of v dv, right? F of v dv, because if you differentiate this, then what you will get, dt by dv is equal to 1, right? And dt is equal to dv, right? So that is the substitution. Then let me scroll it. Then here you see e to the power, from here e to the power minus a into a, that part is constant, so it can be taken out of the integral. So 0 to infinity, then e to the power minus s into v, then f of v dv, right? You can write that way. So here you see, this is nothing but definition of Laplace transformation. This part you can see, okay? And by the definition of Laplace transformation, you can write this result as, so let me, e to the power minus sa. So from this part, this from 0 to infinity integration of e to the power minus sv f of v dv. So you can write this as f of s, or you can do one more thing. So just you can, let us replace 0 to infinity, let us replace v by t, e minus s t f of t dt. So what we have done here, replacing v by t. So according to the definition of Laplace transformation, this part here you can say, this part you can see, this part is nothing but Laplace transformation of f of t, right? And Laplace transformation of f of t, we have taken, you can see here, this is capital F of s, right? So that's why it's going to be e to the power minus sa into capital F of s. So this is the Laplace transformation of f of t minus a into u of t minus a. So that's how we can prove the second shifting theorem. So hope you have understood this. Now let us prove. Now let us prove this theorem. Here you see Laplace transformation of f of t into u of t minus a. Sorry, here not dt. So that's equal to e to the power minus as Laplace transformation of f of t plus a. Okay. So now let us prove this here. So Laplace transformation of f of t into u of t minus a. By the definition of Laplace transformation, you should get 0 to infinity, then e to the power minus st, then the given function, that is f of t into u of t minus a dt, right? You should get that. So now it can be split up into, then 0 to a, then integration a to infinity, right? So 0 to a, e to the power minus st f of t, then you should get here 0 to dt. Why 0? So this function u of t, that's gonna be equal to 0 for t less than a, and it is equal to 1 for t greater than equal to a, right? So that's why, so here in the second part, here you will get e to the power minus st f of t into 1 dt. That's what you will get. So hope you have understood this. Now this whole thing becomes 0. So let me scroll down. So we left with a to infinity e to the power minus st f of t dt, right? So now again we need to do substitution. So let t is equal to y plus a. Suppose t is equal to y plus a, then dt will be dy, and as t tends to a, this y tends to 0, because when y will be equal to 0, then only t can be equal to a, right? Hope you have understood this. Now here you see this result, Laplace transformation of this f of t into u of t minus a. So Laplace transformation of f of t into u of t minus a, that's gonna be equal to now here you see as t tends to a, y tends to 0, so here we will write 0 to infinity e to the power minus t will be y plus a, right? F of t is again y plus a dt, sorry, not dt, dy, right? This is dy. So hope you have understood up to this point. So now here you see, let me change the color. So here the e to the power minus s a, that's going to be constant part, so it can be taken out of the integral. So 0 to infinity e to the power minus sy f of y plus a dy, right? So now just replace y by t, replacing y by t, then what you will get, Laplace transformation of f of t into u of t minus a, integration 0 to infinity e to the power minus s t. So here I missed it, e to the power minus s, this term should be written here, so let me write it clearly. So here you can see that e to the power minus as integration 0 to infinity. So what we have done, this y is replaced by t, so e to the power minus s t f of t plus a dt, right? That's what we will get. Then by definition of Laplace transformation, this part will be equal to Laplace transformation of f of t plus a, and this part is right as it is, right? So this is our this is the proof of our theorem. Okay, so now let us solve this question. So find the Laplace transformation of this function f of t, which is equal to t minus 1 when t is greater than 1 less than 2, otherwise it is 0. So here let me show how to solve this. So here the given function f of t is equal to t minus a, sorry, not a, 1, if t is greater than 1 and less than 2, right? And otherwise it's 0, right? So this function can be written this way also. Let me show you. F of t is equal to t minus 1 into u of, that is the unit step function, t minus 1, and minus u of t minus 2. Now let me explain how. Okay, so if you draw the, now you see by the definition of unit step function u of t minus 1, so it's equal to 1 when t is greater than 1, and it will be 0 when t is less than when t is less than 1, right? By the definition of unit step function. So where you see when you have values, this is 1, this is 0, between 1 and 2, if the value is greater than 1, then function gives you 1, right? This function will give you 1. And when you have greater value than 1 and lesser value than 2, you have value less than 2, for less than 2, this u of t minus 2, by definition this is going to be equal to 0 for t less than 2, right? So this is 1 and here it is 0, so it's going to be again that means when t lies between 1 and 2, this is going to be 1 minus 0, right? 1 minus 0, and 1 minus 0 is nothing but 1, and 1 into t minus 1, that's going to give you t minus 1, right? And otherwise So when you have value beyond 1 and 2, value beyond 1 and 2, that means you have value, suppose lesser value than 1, you have value less than 1, then what you will get? When you have less than 1, then this will be 0, again this one will be also 0, then in that case 0 into anything is 0, so that's going to be f of t will be equal to 0, right? So hope you have understood this. So now let us solve this question. So hope you have understood how we can, why we can write the given function in this form in terms of u of t minus 1 and t minus 2. So now let me clean this page a little bit. So okay, so now let me scroll down. Okay, this is the function. So we are to find a Laplace transformation of this function, right? We are to find a Laplace transformation of this function f of t. So here you see, now we are going to apply the second shifting theorem, right? So second shifting theorem. So here we need to find the Laplace transformation of this function. So according to second shifting theorem, here you see, when Laplace transformation of f of t is equal to capital F of s, then Laplace transformation of f of t minus a into u of t minus a, that's going to be equal to e to the power minus sa into f of s, right? F of s. So we can apply this. So now here you see, you can take the first part only. If you multiply this t minus 1, if you expand this, you will get this result, u of t minus 1, and then minus t minus 1 into u of t minus 2. So now let us take this part only first. T minus 1 into u of t minus 1 comparing with if you compare it with this function f of t minus a into u of t minus a, then what you will get? Here you can see. So here then you will see that in this case we can consider that this is t minus a is this t minus 1. So f of t, we can take f of t is equal to t here. So if you find a Laplace transformation, of f of t, then here you will get 1 by s square, right? Laplace transformation of this t will be 1 by s square, right? So here, and if you compare this function with this, then you will get a is equal to 1. In that case, Laplace transformation of this part only, will be, so let me show you, Laplace transformation of t minus 1 into u of t minus 1 by second shifting theorem. You should get this e to the power minus sa. Value of a is 1, so we will get e to the power minus s, and f of s is, in this case, is this one. F of s is 1 by s square. So our result is e to the power minus s by s square. That's our results. So hope you have understood this. Now let us find the Laplace transformation of this part, second part. We have found the Laplace transformation of this part. So here you can see, to find this the Laplace transformation of this second part, here we are going to compare this one with this f of t with u of t minus 1 or t minus a, I have written here. So in that case, if you compare with this function, then our f of t will be, in this case, t minus 1, and a will be equal to 2. If you compare this part with this t minus a will be 2. So we know that Laplace transformation of f of t into u of t minus a is given by e to the power minus sa, Laplace transformation of f of t plus a, right? Laplace transformation of f of t plus a. So that's what we will get, right? So if you apply that theorem here, then what you will get? So now you can see, so our second part is t minus 1 into u of t minus 2, u of t minus 2. So this is the second part here. So let us compare with f of t into u of t minus a. So comparing with this, we have got f of t is equal to t minus a, so sorry, not t minus a, t minus 1, and f of and here if you compare these two terms, then you will get a is equal to 2, right? So now let us find, to apply this theorem, this is nothing but theorem that we have already proved. So to apply this theorem, so first let us find the you can apply the theorem directly here. So if you apply this theorem, Laplace transformation of here you can see f of t is t minus 1, so you can write this way, t minus 1 into u of t minus 2, that's going to be equal to e to the power minus, instead of as we will write 2s minus 2s, so here value of s will be 2, right? Then Laplace transformation of what we will get, then Laplace transformation of f of t plus 2, that's what we will get. So if f of t is t minus 1, then what will be f of t plus 2? That's going to be e to the power minus 2s, that's going to be equal to Laplace transformation of t plus 2 minus 1, right? So if you put here, if you replace this t by t plus 2, then what you will get, that's going to be instead of t minus 1, you will get t plus 2 minus 1. So our result will be e to the power minus twice s Laplace transformation of t plus 1, that's what we will get, okay? And Laplace transformation of t plus 1, so if what you will get here, so you will get e to the power minus 2s Laplace transformation of t, then plus e to the power minus twice s Laplace transformation of 1, and Laplace transformation of t is nothing but 1 by s square, so here we will get s square, e to the power minus twice s by s square, and otherwise here it will be 1 by s. Laplace transformation of 1 is 1 by s, so here e to the power minus twice s by s. That's what we will get. So here you can see we have got the Laplace transformation of the second part as well. This is the Laplace transformation of second part is this. This is the second part, and Laplace transformation of the first part is this. Here you can see. So if you add these two, let me minimize this. If you add these two results, then you will get the Laplace transformation of this whole function f of t, right? So here you can see clearly this f of t is nothing but equal to this part and minus this part, right? So Laplace transformation of f of t, you can write here Laplace transformation of f of t, that given function is nothing but Laplace transformation of t minus 1 into u of t minus 1 minus, then Laplace transformation of t minus 1 into u of t minus 2, that's what we will get, right? So Laplace transformation of f of t, this is the f of t, and it can be written as this part minus this part. So here we can clearly write that Laplace transformation of this function is nothing but Laplace transformation of this part and Laplace transformation of this part. So doing that, we have got this, and Laplace transformation of this part we have already evaluated here. We have already got it, that this is the result, okay? So e to the power minus s by s square, right? So let us put here e to the power minus s by s square, and here, sorry, minus, and Laplace transformation of this part is this. So e to the power minus 2s by s square plus, and that's going to be again minus, and because of this minus sign, so minus e to the power minus twice s by s. That's what we will get. Now if you simplify this, then what you will get? So if you simplify this, then you will get, so let me scroll down the page, e to the power minus s minus e to the power minus twice s by s square minus e to the power minus twice s by s. That's what you will get. So that is our result. So let us solve one more question. Now let us find the Laplace transformation of this function. So here you see this function, that u to t, it means this is nothing but 1 when t is greater than 2, and it is 0 when t is less than 2, right? So that means you can write u of t minus 2, right? That's the meaning. So our function is t2, sorry, not 2, t u2 of t. That means it can be written as t into u of t minus 2, right? So now let us find the Laplace transformation. Laplace transformation of t u2 of t, that's going to be equal to Laplace transformation of t into u of t minus 2. So then what you will get? So again we are going to apply this theorem, that Laplace transformation of f of t into u of t minus a, that's equal to e to the power minus as or sa, whatever, is Laplace transformation of t plus a. So let us apply this theorem. So here if you compare this function with this function, here you can see our f of t is nothing but t. Our f of t is t, right? So so here you see, then value of a is equal to 2, right? Value of a is equal to 2. So then if you apply this theorem, then our result should be e to the power minus twice s, e to the power minus twice s Laplace transformation of t plus 2. So if f of t is 2, then f of t plus 2. So let me write here f of t plus 2, f of t plus 2, right? F of t plus 2. If our t is f of t, then f of t plus 2 will be e to the power minus twice s Laplace transformation of t plus 2, right? So it's simple now. E to the power minus twice s Laplace transformation of t, then plus e to the power minus twice s Laplace transformation of 2. 2 means you can consider 2 into 1, 2 is constant. So here you see Laplace transformation of t is s square, 1 by s square, so you will get e to the power minus twice s by s square, then plus e to the power minus twice s, and 2 comes out, and Laplace transformation of 1 is 1 by s. So this is your result, and you can take t to the power minus twice s as common, then what you will get, our result will be e to the power minus twice s 1 by s square, 1 by s square plus 2 by s. So this is our result. That's what Laplace transformation of f of, sorry, not f of, t into u2 of t, right? u2 of t. So this is the Laplace transformation. So hope you have understood. So hope you have liked the video, and if you have liked the video, please hit the thumbs up button and share with your friends. If you're new to my channel, please subscribe the channel and hit the bell icon.